To see the gyrocompass effect, we have a following arrangement. We have a flywheel or spinning disc which will be able to rotate with angular speed omega s. And this disc is put in a frame represented by these red lines, and this frame is supported by support base A and B. So what we can also see is that this frame can rotate freely about AB axis, and this support vertical rods, they are put in a rotating platform which itself can rotate with angular velocity omega, and this is about the vertical. Now let us try to look into the picture details with our vector notations. So this green vertical line shows the rotation axis of the bottom support rotating platform with angular velocity omega. Now this spinning disc will be getting one angular momentum vector which is represented by this red arrow, and what we can see is that this red arrow can take any angle with respect to the vertical direction, which we will be representing by theta. Now angular momentum Ls precessing about the vertical axis. So we can imagine a torque which we can write in terms of omega cross Ls, so which is going to be omega Ls sine theta. And what we see is that this is going to be balanced by I alpha, which will be nothing but I d2 theta by dt square. And also we see that torque is going to be 0 when theta is equal to 0. So that is going to be basically your equilibrium position. So essentially this is going to be a second order differential equation showing is the simple harmonic oscillations, and oscillation frequency is going to be given by root of omega Ls by I. These oscillations will be there if there is no friction between the frame and the support rod. But if there is a friction, then ultimately angular momentum will align in the direction of vertical axis. Basically L is going to be parallel to omega. And that's why we say it gyrocompass, because Earth itself is rotating about its axis. So if we have a high spinning disk, the disk will try to align its angular momentum along the Earth's north-south axis. Here we have a small rotating platform which can rotate clockwise and anti-clockwise. On top of that we are putting a small cardboard piece so that we can make it wider, and this is powered by a USB port of a computer. Here we have our spinning disc mounted on a frame of PVC pipe, and which can rotate about this black horizontal axis. So this is going to be our experimental setup. So now we will spin it just like a top. Now we place it on rotating platform. You can see that green side of the disc is up. As soon as the platform changes its rotation direction, now pink side is up. Once again, green side is up. Pink side of the disc is now up. This we expect because angular momentum will try to align with the omega of the rotating platform. Let us repeat the experiment. Once again we give rotation and place the frame on rotating platform. Now we see green side of the disc is up. When it changes, now pink side of the disc is up. So basically what we are seeing is that angular momentum of the disc is trying to align itself in the direction of omega of the rotating frame. Of course, our angular momentum, speed omega is not that large, so we do see little bit of oscillations and deviation from the vertical direction. Let us repeat once again. You see pink side is up, and now it will flip, green side goes up. So I hope this is able to show the gyrocompass effect, and we do see that angular momentum tries to align with the capital omega of the rotating frame.